How does weather affect satellite communication signals? Have you ever wondered how rain, humidity, or even thunderstorms impact the signals that satellites send and receive? Weather plays a significant role in satellite communication, affecting how well these signals travel between satellites and ground stations. Let's break down the various weather factors that can influence satellite communication signals. First up is rain. It is the most impactful weather condition when it comes to satellite signals. Raindrops can absorb and scatter electromagnetic waves, which leads to a reduction in signal strength known as attenuation. This effect is particularly noticeable at higher frequency bands, like K-band and QV band. These bands have shorter wavelengths that are similar in size to raindrops, making them more susceptible to signal loss during heavy rainfall or steady downpours. Next, we have humidity and water vapor. Water vapor in the atmosphere can reflect and refract radio waves, which weakens or scatters the signals. Changes in humidity levels can cause fluctuations in signal quality, resulting in spotty or intermittent connections. Unlike temperature changes, moisture content is the main factor that affects signal reliability. Cloud coverage and fog also play a role. Dense clouds and fog can scatter radio waves, increasing the path loss between the satellite and the ground receiver. This scattering delays the signal and reduces its strength, causing disruptions. High winds can make things worse by moving ground antennas or putting stress on satellite equipment. Thunderstorms bring another layer of complexity. Lightning can create electrical interference that degrades signal quality in both uplink and downlink directions. It can also damage outdoor satellite equipment, leading to local service outages during storms. The impact of weather on satellite signals heavily depends on the frequency band used. Lower frequency bands, such as L-band and C-band, have longer wavelengths that are less affected by rain and atmospheric moisture. However, they offer lower data throughput. On the other hand, higher frequency bands provide greater bandwidth and higher data rates, but are more vulnerable to weather-induced attenuation. This trade-off is essential in designing satellite communication systems, influencing antenna size, power needs, and error correction techniques. To combat these weather-related challenges, satellite operators employ several strategies. Frequency diversity allows them to switch between different frequency bands to avoid those affected by weather. Adaptive modulation and coding help adjust signal parameters dynamically to maintain link quality. Power control can increase transmission power during adverse weather to compensate for signal loss. Advanced weather forecasting is also used to predict conditions and proactively adjust satellite operations to minimize disruptions. In summary, weather affects satellite communication signals mainly through rain-induced attenuation, water vapor scattering, and atmospheric interference. The severity of these effects depends on the frequency used and the intensity of the weather. Understanding these factors is essential for designing resilient satellite systems and ensuring consistent connectivity, regardless of the weather conditions.